So in this video clip, I'm going to run through some code, C++ code for estimating the Greeks. That's delta, gamma, vega, theta, and rho. For the Black-Scholes call and put, we are going to include a dividend yield. The code originally I obtained from Fabrice Roy on his website. Philupta, that website is now defunct, but I have the code here. And just to note, when you run C++ in Google Colab, you post it up to your content folder and then you run it separately from the IPYNB notebook. So just to see that in operation, what we have here is we use Boole's rule to estimate the normal cumulative probability. We invoke that then in the Black-Scholes estimation, usual set of parameters S, K, R, Q, T, sigma. Here is the V, is the volatility, and then the option type, whether it's a call or a put. Might note that D is D1 and D2 is so the call is estimated S E negative QT ND1 minus E negative RT K ND2. Now the D2 here is D1 minus sigma square root of T. So we don't explicitly put in D2 or D1. We just put in the normal variate. It's not referred to as D1 here, but if you look at the other code in the Colab that I have here, and I'll share the link to this Colab so you can verify against the formula that I've posted in the Python notebook. You'll notice that the two align to each other. So D here aligns to D1 in the formula that I set out earlier in the Colab. Notice also we're invoking put call parity. Again, I leave a link to that explanation of put call parity underneath the video clip. And then we have our delta, our gamma, vega, theta, so rho, and then theta estimated. So if we execute, we run the cell and we load in our parameter values, so 100, 1 year, the risk-free rate is 5%, dividend is 0, volatility 20%. We'll output the value of the put, the delta of the put, the gamma, the vega, theta, and rho of the put. So, okay, so this is two-stage. You execute the C++ um, in the code cell. You'll note that if you go into the content folder, the code now is posted here. So there in full. And then to execute the code, one more step, we run our G++ main, name of the file is main.cpp. And we estimate the value to call, sorry, the value of the put. So value to put, the delta, the gamma, the vega, theta, and rho. We can verify the results against the JavaScript we had used before. So if we were to compare like against like, to 557, if I copy these values, we compare against the estimates we had performed earlier. So the same parameter inputs as before. Again, I'll leave the link to this Google Sheet where we run the our code. But we can notice here if I take the call, that might be the easiest way to do this. Control C and go into our we can put into a text cell or a code cell here just underneath. Control V. We can see that the value of the put aligns. The delta of the put, same as the 363169. The value of the gamma is consistent. The Vega is 37, 3752. Theta negative 165788. So the job and the row is also the same. So they correspond to each other. Now, if we want to run uh, and output the value of the calls, just change P to C, capital C. We run our code artifact again, and we're writing in, so we've overwritten, if you like, the main CPP. If we double click here and take a look, that's what's in there. You'll notice we've changed P to C. So it's now become C. So for the call, and then if I come down into main, so this time it's going to be for the value of the call, run it again, and we now output the value of the call, the delta of the call, the gamma, the vega, the theta, the rho, and that's going to be consistent with our JavaScript generated Google Sheets results that we have here, and I'll leave the link underneath the video clip. And I'll leave a link to the code cell where we've run the C++ code in our Google Colab. So notice that the 1045 aligns, the delta is consistent, the gamma of is the same for both call and put, the Vega is both the same for the call and put, 3752. Um, Theta is for the put is -16. So for the call is -641, -641, and row is for the put, sorry, for the call is 53, 53, 23. So they're in agreement. Okay, so that's it.